with Cat B King. I've been approximating sums, Euler's method, using step size and the first derivative, partnering up and doing board work. James just got a 5 and we know it'll be his first. Euler's method, Euler's method. I've been approximating sums, Euler's method, using step size and the first derivative.
Real life application, national debt burden, needing a solution. Euler's ends the burden, predicting deficits, changing rates of college. Trump or Hillary is gonna end up needless knowledge.
Finding y sub n plus 1, always working hard. I'm a mathematician, call me Leonard. Universal step size, jot it down on a note card. Using a tangent line, cruising up Cal Boulevard.
Same idea as slope fields, approximating differentials. To his 13 daughters, he was always influential. May have been blind, but still kept his credentials. Euler's success was always exponential.
Using initial condition and a step size, I've been approximating steps so I get the prize. Plugging previous points to the first derivative. If you ain't doing Euler's, then you ain't even lived.
I've been approximating sums, Euler's method, using step size and the first derivative, partnering up and doing board work. James just got a 5 and we know it'll be his first. Euler's method, Euler's method. I've been approximating sums, Euler's method, using step size and the first derivative.
Euler's method is a process that can be used when you don't have a function you can solve. His thinking included that you direct yourself with the differential, slide, and then redirect yourself using the point that's on that tangent line. There is a growing error in this method, as the more you slide and redirect, the farther away from the actual function you are. These two images can help display the process. In using Euler's method, a new notation comes about that expresses a differential equation as a function f of x comma y. It can be looked at as a slope, which is where we get the equation written by Taylor Eisler.
The slide that Dakota mentioned earlier is referred to as the step size in the method and is defined as h. This is what the denominator was in the previous equation. Therefore, we can rewrite it as follows, which Cindy is rewriting.
The common form for the Euler's method equation is Euler's method is a recursive process, which means we can't take step 3 before we take step 2. It requires a differential equation,
An initial condition,
A step size,
and an interval.
Example 1 involves using Euler's method with a step size of h equals 0.1 to approximate the solution of the initial value problem y prime equals y minus x, with the initial condition y of 0 equals 2, and it's over the interval 0 to 1. Now that we have all our information, we can use Euler's method equation, which is and we will slowly muddle our way through this tedious process. We will begin at n equals 0, which is our y sub 1, and use our initial condition to begin finding values of y.
Alright, so I'm going to go through and briefly explain what Taylor did on the board here. First of all, we wrote down our Euler's method equation. Now, for our n equals 0, we got y sub 1. Our 2 came from our initial condition, which was y sub 0. Our 0.1 came from our step size, h, and this value came from plugging in the initial condition, so you can differential equation seen here. So 2 minus 0 is 2. So, with that being said, we get our xy coordinate for the first slide step, which was 0.1 because we moved over our step size of 0.1. And then the 2.2 came from evaluating all of this. Then, for n equals 1, finding y sub 2, we put in our 2.2 found from y sub 1 here, our same step size, h, and we plugged in this point now, 0.1 and 2.2, into our differential equation to get this value. Then, moved over 0.1 step size to get 0.2 as our x, and our y came from y sub 2 here. The same step was followed for n equals 2, n equals 3, n equals 4, n equals 5, all the way down to n equals 9, which gave us this value.
Now that we have approximated our value for y of 1, which was 4.537-ish, we can solve the initial value problem, which is a first-order linear differential equation, in order to find the exact value of y of 1. To do this, we're going to use these three equations that work with first-order linear differential form. Once you muddle through all that, you come down to find that the real y of 1 equals 4.7183.
Now we're going to use Euler's method to approximate the same differential equation, y prime equals y minus x. Our initial value will remain the same, y of 0 equals 2, and it will be over the interval from 0 to 1. Now we're going to solve this differential equation with a step size of 0.2 instead of 0.1 to see the variation in approximations. As you can tell, a larger step size leads to a less accurate approximation.
When solving the actual differential equation, we get that y of 1 equals 4.7183. Using Euler's method with a step size of 0.1, we get y of 1 is approximately 4.5937. And using a step size of 0.2, we get that Euler's method is approximately 4.4883. As we can see, using a smaller step size gets us to a closer approximation of the actual value.
Well, just until we get it done. Stop. Put it
Bloopers.
correctly. No, that camera quality is not as good.
Now you have to hit the... Guys, jot it down on a note card. Also, using it. Guys, jot it down on a note card. Also,
Jot it down on a note card.
You did what?
I swallowed a bug. Okay, this is actually really weird. Let's not do this.
Yeah. Now we're going to use Euler's method to approximate the same differential equation, y prime equals y minus x, with an initial y value.
Okay, pause.
And then we'll cut it out.
I've been approximating sums, Euler's method, using step size and the first derivative, partnering up and doing board work. James just got a 5 and we know it'll be his first. Euler's method, Euler's method. I've been approximating sums, Euler's method, using step size and the first derivative. Calc, B, C with Kathy King.